All right, let's talk units and systems, because those two things, when I was first introduced to them, were confusing and overwhelming, I'll be honest. I mean, look at this list, it's quite overwhelming. And then, especially systems, just the idea of what a system meant to me was difficult to understand. So we're going to clear all of that up immediately, because units can actually be a cheat code, and systems are essential to understanding work and forces. So, let me explain how units help you. So here's first of all just a list of all what units stand for and everything about units. You have displacement as measured in meters, velocity meters per second, acceleration meters per second squared, all the way down the line. There's a few of those though that have ulterior meanings of just simpler words, like for example forces, energy, power. Those ones have um, those ones have their own name that we call imperial units because those ones are imperial measurements that aren't exactly adhering to the metric system of measurements. Forces, the imperial measurement is newtons, the one that you would write down on tests, but an equally acceptable one would be kilograms per meters per second squared, which actually makes sense because we know Newton's second law says force is equal to mass times acceleration. If force is equal to mass times acceleration, if we break down all the units of mass and acceleration, we get kilograms times meters per second squared, which is exactly what a newton is. So this is the same exact way that units can actually be a cheat code for you. If you forget exactly what significance things hold, you can break down the unit of whatever you're dealing with. So let's say you're trying to deal with energy. We know that energy is kilogram per meter squared per second squared, which would be a joule. So if you forget for a second, like, wait, what's the equation for kinetic energy again? And you remember that there is some significance kinetic energy holds with mass and then also velocity. If you remember that kinetic energy is some combination of mass and velocity, but you don't know if they're squared or whatever, you can just think to yourself, oh wait, a joule is kilograms per meter squared per second squared. And if kinetic energy is some variable x or y of this kinetic energy here, you can think to yourself, how do I get these two numbers to equal this? Well, mass is already in kilograms. We can leave this as a power of 1. Velocity is meters per second. So how do we get meters per second to equal meter squared per second squared? We square the whole thing. So that means that this x here is equal to 2, which is exactly how kinetic energy works. Although, except there's also 1/2, which is just you just have to remember that there's a 1/2 there for kinetic energy. And that actually applies for all the different types of energies. Um, for example, you also have gravitational kinetic, which is equal to mgh, well, mass, kilograms um, per gravity, which is meters per second squared, per height, which is meters. Well, there you go. You have 2 meters there, so this becomes a meter squared second squared. So there you go. That's a joule. And then it also works for elastic potential energy because we know that elastic potential energy is 1/2 kx squared. So we have a 1/2, which is not useful to us. We have a k, which is a newton meter, or newton per meter, times meter squared. Okay, well then let's break everything of this down. We know a newton is a kilogram per meter per second squared, and then we divide it by a newton, we get kilogram second squared, and then add meter squared, we get kilogram per meter squared per second squared, which is exactly what the energy would be. So now we also can think of power as the amount of joules energy per second, and the imperial measurement for that is a W, a watt. And then we also have momentum, which is kilograms per meter per second, not squared, because we also know that momentum, little p, is equal to mass times velocity. Instead of being mass times acceleration, we just divide it by a second. Instead of mass times acceleration, we divide it by a second, and then we have meters per second now. So, and that can also clear up some stuff that we can say, how is momentum related to force? Well, we can say momentum is related to force because if you look at these two, force is kilogram meters per second squared, momentum is kilogram per meters per second. So if we know that momentum is kilogram per meters per second and we wanted to get it to equal meters per second squared, we can say change in momentum over change in time, because time is that missing seconds, is equal to our force. And that is indeed an equation for force given momentum and time. So now let's look at this other column here. We have now all of the angular stuff. And I'm going to use a different color because it's all angular. So we have radial displacement is measured in radians. We have angular velocity, radians per second squared, angular acceleration, radians per second, or radians per second squared, angular velocity is radians per second, not squared. Moments of inertia, which is kilograms per meter squared. And then we have torque, which if you'll notice is actually the same exact unit as energy. But the difference between torque and energy is that torque acts in a direction. So torque is actually a vector and energy is a scalar quantity because energy just describes the amount of energy in a thing. It doesn't matter how moved or what direction the energy is. It's just always, it'll always be, regardless of whether the thing is moving that way, that way, that way, or that way, it'll always be whatever it is. But torque actually matters. So difference between vector and scalar, of course, is just, does direction matter? So now we can also do linear momentum. Linear momentum is kilograms per meter squared per second. So if you'll notice the difference between all of these is that it's really just meters squared. And then with the exception of torque being the same as energy. But the only differentiation then being that one is a scalar and one is a vector. So we can also do the same exact thing we did for all of these things over here, but for our units instead, and use those as a cheat code, except radians work a little bit differently. Radians talk about motion around a circle. So a total one circumference of distance would be 2 pi, and then if you stop here, it'd be pi. So, and then counterclockwise, not clockwise, is normally the direction that positive would be. It just depends on how a book would specify it. So radians work a little bit differently in a way that if you were to multiply a radian by an actual measurement like meters, you completely negate the fact that there was ever a talk of radians. So basically, if we wanted to convert angular velocity into actual velocity, you could say that, and then what do we need to do to multiply this to get meters per second instead? Multiply it by meters. So displacement is equal to our velocity. And that is indeed an equation for it. And then subsequently, you could also say angular acceleration times distance is equal to meters per second squared. So actual acceleration. So this is actual equations you could use to try to solve for things. You could also say velocity. So angular velocity divided by time gives you displacement. So angular velocity times, I don't know, you could do angular velocity times displacement over time would be equal to displacement, because that you'd be left with just radians, because W divided by T is just radians. If you look at the units and then multiplied by an X, you would be left with only displacement. It's just, you can use the units as almost a cheat code to solve for actual things. And all of these units here are backed up by their actual base equations. Like, for example, moment of inertia is some constant times mass times radius or length squared, which makes perfect sense because mass is kilograms, radians squared would be meters squared. And then this constant is just dependent on the type of object we're dealing with. And is determined through calculus, which we don't have to do. So we also know that linear momentum L, is equal to moment of inertia times angular velocity, not angular acceleration. So if we know that linear momentum is that times that, we know this is kilograms per meter squared multiplied by radians per second, which makes sense because then the radians disappears because it's being overtaken by the fact that we're talking about meters. Kilogram per meters squared per second. That makes sense because we know that our units for linear momentum or angular momentum, if I've been saying linear for this L, I mean to say angular momentum. I just see the L and think linear is that. So we can also justify torque that way. Torque is equal to I times A. So then we'd go through the same process just to find out that instead we're dealing with seconds squared. So we can really use all of those as cheat codes. So now we can also talk about things that are in oscillatory motion. So things that'll bounce back up and down or go back side to side like a pendulum or a spring. So if we have period, we just have to know that the period is the amount of time it takes to complete one full oscillation. So that means if we're dealing with a spring, it would mean that if the spring was at maximum stretch, if it had to go back down and then back up, the amount of time it takes to do this motion, assuming that and that are maximum stretch, is one period. And then we also know that frequency is 1 hertz. And hertz are measured in the units 1 over seconds, so 1 over time, which makes sense because frequency is also equal to 1 over the period. So there you go. Except we know frequency more as hertz. And you also know that the higher the frequency, so if you have a greater frequency, you would have squiggles that are very close together, which means it repeats very often. So if you have a lower frequency, you would have squiggles that don't repeat as often. So, I mean, and that could be proven by the fact that we use the units for it. And then we also have to know that amplitude is just the distance from the middle of the line to the top or the bottom. So that means the entire distance traveled from top to bottom is 1/2 amplitude. And amplitude is measured in normally meters because our oscillatory motion in physics are talking about things that actually oscillate back and forth in real life. So if it were a pendulum, it would be back and forth from here, where the distance from here would be your amplitude if a pendulum is going back and forth this way. Or if you're talking about a spring, you would have maximum stretch right here. The distance from maximum compression to maximum stretch is 2a, meaning that the distance from here is a. And we know that normally because the equilibrium point is halfway through the maximum and minimum amplitudes. Now, let's talk about systems, because systems are paramountly important to understanding how forces and energy works. So we also know that energy is dependent on forces. So if we talk about how it's mainly interacting with forces and how it's mainly we can also figure out how it's interacting with energy. So you've probably seen this diagram before, except I included k-rotational this time because we're talking about everything. This diagram basically is the difference between a closed and an open system. So, work describes an amount of energy added or subtracted to an equation. And if you don't know the equation for work is equal to force times distance, not time. That's impulse, which is different. We know that work is equal to force times distance. So if impulse is equal to force times distance, that makes sense because our equation checks that out perfectly. Force times distance would be newtons per meter, which is exactly what work is, joules, newtons per meter. I mean, torque shows you that as well. So if we know that, then we can try to then work with work here. So when we know that that's our work equation, we can think about how if we are applying a force to a system over a set period of time, then we have a change in work or a change in energy. Not a change in work, a change in energy to the entire system because work is a unit that describes energy. So if we are then dealing with work in this way, then Now let's talk about systems, because systems are paramountly important to understand how forces and energy works, and whether or not we can actually get changes of energy. So let's say, for example, we have a system where we have a ramp that doesn't have friction and a box on top. So if we say that the only system we're going to describe is the box, so I'm going to circle this in blue. The only system we're dealing with is the box, then we're going to get a change in energy as this box moves down the hill due to gravity, because gravity is not part of the system. We are going to have a change in energy in some way, shape, or form because gravity is acting outside the system and therefore doing work to the system. Because if the box is the only thing that we're talking about here, then gravity will accelerate it. But if we talk about the box and Earth system, so the system that is just, or the system that is the box and the Earth, so therefore the entire thing, then gravity is an internal force, meaning that energy stays constant the entire time because there's no friction. Meaning that the amount of gravitational potential energy would be UG equal to our final energy, K. Now, if we said our system was just the box, it would seem like energy is appearing out of thin air because, of course, the only energy that matters when a box is the only thing in your system, a box on a hill like this is the only thing in your system. Let me grab the correct colors. If a box is the only thing that matters, then you're going to see gravity pull that box down, and then all of a sudden this box starts gaining speed. Originally, if the only system here is the box, we don't have to care about a height, but now because it is on an incline, we see it suddenly start to gain speed from being at rest, and therefore we get a change in energy equal to gravitational potential energy, which essentially is the same exact thing as if you were to talk about it with a system, or with the system including the Earth. But we just have to keep in mind that if you have a system like this, where you have the box here, and if you have the box here and the entire system is the box Earth system, if the entire system is the box Earth system, that's a horrible letters, but I don't care. If the entire system is the box Earth system, energy stays constant, especially because there's no friction on this ramp. But if there isn't Earth included in the system, then energy does not stay constant. And that's really the key part to understanding it all. So if we then included another thing that said that there was friction in there, let's say there's friction on this rough incline. I keep erasing it just because, like, out of habit. So if we now have friction on the incline, friction is a form of non-conservative work. The difference between conservative and non-conservative work is conservative work will transfer the energy to one of these other three things. But non-conservative work will convert it into something that it can't be converted back into one of these other things, like thermal, like sound, or like thermal, sound, and friction. Those are the three, really. So in other words, heat and sound are the main two, and I'm probably forgetting one other, but you can probably just assume that if it's not one of these, then therefore it's non-conservative work. So that means that what we're going to get is we're going to start with a sum of energy that then will be detracted by the work done by friction. So then it'll be equal to the sum of energy at the very end. Now keep in mind that I'm using sum of energies here, and we would talk more about that in the energy videos on why exactly this equation is very useful. But keep in mind, though, that work actually acts as a vector too. So really, you're always adding work. But the thing is, because friction is acting in the opposite direction that it's moving, that it then becomes minus. It's slowing it down. Whereas if we somehow made this a non-friction ramp, and then we were adding a force here across the entire distance of this ramp until it hits the bottom, let's say this ramp is length L, then we would be adding a force equal to the force times the distance it travels, which would be work, proven by the units. So really, this all connects in the way that we have systems here that would and wouldn't have additional things. Now, it would also be different if the fact that we were including the force in the equation, but we're not even going to deal with that. So, or the force included in the system. But yeah, really the only major distinction between systems that would be good to understand is where to section them off. Because another thing too is if we have a system that has multiple parts, like let's say we have two boxes on a string. Um, if we have two boxes on a string that is pulled taut, then we have like let's imagine this a separate way, so that way we can compare this better. So let's say we have an upward two boxes where the top box is fixed to the um, wall behind it or something like that. So, and the bottom box is left to hang freely. So if we talked about just this box one, we would have all the forces on box one described as the tension that pulls it down, the gravity that pulls it down, and the normal force from the wall or the holding force from the wall pulling it back up. And because this box is not moving or rotating, we know that all the sum of the forces is equal to 0. Now, if we were to also talk about only box 2, we have a tension force that pulls it up that's equal to the tension force box 1 is being pulled down by. And then we also have a force of gravity that pulls this box down here. So if we were to then describe this whole thing as one system, we would have a weight equal to the addition of both these boxes, assuming that this string here has negligible mass. We would have a weight here that's equal to both of the boxes combined, and then a normal force, because the boxes are not moving, equal but in opposite direction to the gravity that pulls it down, to the weight of the boxes. And of course, I'm saying normal force, but it's really just the force applied by the wall that allows it to stay fixed, which I guess would be a normal force. So because of that, we can define our system as these two, and then notice that I didn't use tension at all in this system thing, because all the forces on the inside, they canceled out if we involve tension on the entire system level. So the work done by tension here is essentially 0. But if we were to also use one of these systems as well, we would have also work done by tension equal to 0, because these two would then cancel it out, and then these two would cancel it out. But for instance, let's say that they're still pulled taut, but then all of a sudden this gives way. You would have tension pull this box down, and then there would be work done. Or tension pull this box up, and then there would be work done, or something like that. But of course, if you were describing both the systems, the tensions would cancel out from one another. And that's really why learning the systems is so important, because if you are talking about a system of objects, like let's just say system of objects where one of them is on an incline, or I don't know, something like that. But if we're talking about a system of objects like this, then if you have forces that act between the objects, like the tension in this wire here, that's a horrible arrow. You have tension between these two here, then it's completely negligible and not necessary to talk about if it's just this system. Although if you're talking about just this box, we need to know it because it's an external force. So that's really the gist on how systems work, and also how units are connected to systems.